In this example, we're asked to find the volume of the solid bounded by the cylinders x squared plus y squared equals to r squared, and y squared plus z squared equals to r squared. By symmetry, instead of working on all 8 octants where the volume of the solid lies, we can only work on the first octant and then multiply the volume that we find on the first octant by 8 to find the total volume of the solid. First of all, let's sketch the region D that the volume of the solid lies on the first octant. So we see that the region D is bounded by the quarter circle x squared plus y squared equals to r squared that only lies on the first octant, and then the x and y axis. So the meeting points of that quarter circle with the x and y axis are the points r0 for y equals to 0 and 0r. We can set either a type 1 or a type 2 integral, but let's work with a type 2 integral in this case. So we see that the left boundary will be the y-axis. So in that case, x equals to 0. And the right boundary is the portion of the circle that lies on the first octant. So if we solve for the x squared plus y squared equals to r squared, we'll get that x equals to the square root of r squared minus y squared. So x is always positive, so we only take the positive root. Also, on the first octant, we have that y is between 0 and r, with 0 and r included. So the domain of the type 2 region is the set of all points x comma y, such that x is between 0 and square root of r squared minus y to the square, and y is between 0 and r, with 0 and r included. Since we are working on the first octant, that means that z will be either positive or 0. Therefore, if we solve the other circular cylinder equation with respect to z, we'll have that y squared plus z squared is equal to r squared. So that means that z squared is equal to r squared minus y squared. And since z is always positive or 0, we'll get that z is equal to the square root of r squared minus y squared. So we can go and set up the volume of the integral, the volume only on the first octant. So this volume V1 will be equal to the integral from 0 up to r for y, and then the integral from 0 up to square root of r squared minus y squared of z times dx dy. So this will be equal to the integral from 0 up to r, and then from 0 up to the square root of r squared minus y squared of z, which is equal to the square root of r squared minus y squared times dx dy. So that is equal to the integral from 0 up to r. And now integral of square root of r squared minus y squared times dx is equal to x times the square root of r squared minus y squared. And this, we need to evaluate that between x equals to 0 and x equals to the square root of r squared minus y squared times dy. So that would be equal to the integral from 0 up to r, setting x equals to r square root of r squared minus y squared will give us square root of r squared minus y squared times another square root of r squared minus y squared. And then for x equals to 0, we get a 0 times dy. So that is equal to the integral from 0 up to r of just r squared minus y squared times dy. And if we evaluate the integral, we'll have r squared times y minus 1/3 y to the third. And we need to evaluate that between y equals to 0 and y equals to r. So that will give us r squared times r is r to the third, and then we have minus 1/3 r to the third. So this is equal to 2 r to the third over 3. Therefore, the volume in all 8 octants will be equal to 8 times the volume in the first octant. So we have 8 times 2r to the third over 3. So therefore, the volume in all 8 octants will be equal to 16 r to the third over 3.